Hello everyone, I am Dr. Krishna Sarker. Here in this session, I will be going to discuss about Routh stability analysis and example number 2. This is linear control systems, lecture series on linear control systems, lecture number 33. So our new topics, Routh stability analysis, example 2. Solved example, Routh Hurwitz Criterion. Example number 2. A closed loop control system has the characteristics equation given by s cube plus 4s square plus 100 s to the power 1 plus 500 equals to 0. This is the characteristics equation. What is the characteristics equation? 1 plus g of s into h of s equals to 0 is called characteristics equation. And s cube plus 4s square plus 100s plus 500 equals to 0, third order polynomial equation. Investigate the stability using Routh Hurwitz criterion. So investigate the stability using Routh Hurwitz criterion. Then solution. Step 1. The given characteristics equation is, what is the characteristics equation? S cube plus 4s square plus 100s to the power 1 plus 500 equals to 0. This is the characteristics equation, and order of the system equals to 3. So this is the third order system because s cube, and coefficient of s cube. What is the coefficient of s cube? S cube coefficient equals to 1 because this coefficient equals to 1. Then s square coefficient, this is the s square coefficient equals to 4. This is the s square coefficient 4. Similarly, for s to the power 1 coefficient is 100 because this is 100, and s to the power 0 coefficient is 1. So coefficient of s cube, s square, s to the power 1 and s to the power 0. Then step 2, necessary condition for stability. What is the necessary condition? What is the necessary condition? Let us consider a system with characteristics equation is s cube plus 4s square plus 100s plus 500 equals to 0. It can be stated that the necessary conditions for stability of a system are as the characteristics polynomial have all the coefficients real and positives. This is the characteristics equation, and all the coefficients, that means 1, s square coefficient 4, s coefficient 100, and s to the power 0 coefficients 500. All the coefficients real and positives. So first condition satisfied. Then next condition, none of the coefficients of the polynomial is 0. In this case, s cube coefficients, s square coefficients, and s to the power 1 coefficients and s to the power 0 coefficients of the polynomial not 0. That means none of the coefficients of the polynomial is 0. Then next point, this is also satisfied. None of the powers of s between the highest and lowest power of s is missing. In this case, s cube, s square, s to the power 1, s to the power 0. So s cube, s square, s to the power 1 and s to the power 0. No missing power in this polynomial equation. The necessary conditions are satisfied. So these three conditions are satisfied. That's why necessary conditions are satisfied. It is to be highlighted that These are only necessary condition but not sufficient. All stable system must satisfy this condition. For a system or for a stable system, these three conditions are satisfied actually. But system satisfying all these conditions need not be stable. So next step, necessary condition. The necessary condition help us to eliminate polynomial with negative coefficients or missing power of s by visual inspection only. This is also very important sentence. If the characteristics equation satisfies all the necessary conditions, it is a possible nominee for examining further for stability. Then Hurwitz and E.J. Routh have independently established the conditions for stability of a system without actually finding out the roots. The criteria is as known Routh Hurwitz Criterion for stability. So this criteria is known as Routh Hurwitz Criterion. This criteria determines how many roots of the characteristics equation in the right half of S plane. This criteria determines how many roots of the characteristics equation lie in the left half of the S plane. If this is imaginary and this is the real axis, in this criteria determines how many roots right hand side. This is the right hand side. And if all the poles and zeros left hand side of the S plane, then system will be stable. This test also determines all the roots on the j omega axis so that their multiplication can be found out. And the polynomial coefficients are arranged in an array called the Routh array. Then sufficient condition. What is the sufficient condition? Next step. Sufficient conditions, Routh Stability Criterion, Routh Stability Analysis. Step number 3. S cube plus 4s square plus 100s to the power 1 plus 500 equals to 0. This is the polynomial third order differential equation or third order equation. The Routh array is constructed as follows. Each row is identified in the descending order of power of S. The first row contains coefficients of alternate power of S, starting with the highest power S cube. In this case, the starting highest power of S cube. And the second row contains coefficients of alternate power of S, starting with the second highest power of S square. In this case, second highest power S square and the coefficient 4. Then the other rows are constructed in a systematic way as indicated in the procedure given below. So step number 4, what is the step number 4? First, rearrange. Arrange all the coefficients of equation 1 in 2 rows. Row number 3, S cube, and this is the 1 and 100 alternating coefficients. This coefficient 1 and this is the 100. And next row 2, S square and the coefficients 4 and 500. This is the 400, 4, and this is the 500. S to the power 0 coefficients. This is the 500. So 2 rows. Then construct the Routh table, Routh Stability Criterion, and this is Routh table. Row 3, S cube 1 and 100, row 2, 4, 500. From these 2 rows, we then subsequent rows to the Routh array. Row 3, S cube 100, row 2, 4 and 500s. And row 1, S to the power 1, A, B. Row 0, S to the power 0, C and D. So calculate A, B, C, D. Calculate A, B, C, D. What is the magnitude or value of A? So calculate A. A equals to 4 into 100. A equals to 4 into 100. Again, A equals to 4 into 100. So write down 4 into 100. Then minus 1 into 500. 1 into 500. And divided by starting point 4. This is 4 and this is equivalent to minus 25. So A equals to minus 25. Then calculate B. B equals to 4 into 0. This is 4 and in this position 0. So 4 into 0 minus 1 into 0. 4 into 0 minus 1 into 0. Write down 4 into 0 minus 1 into 0 divided by 4. Starting value 4. This is 0. Then C. C equals to A into 500. C equals to A into 500. A equals to 20 minus 25. C equals to this into this minus this into this. So A equals to C equals to minus 25 into 500 minus 4 into B equals to 0 divided by minus 25 minus 25 cancel out and 500 only. Then D equals to again 0 because A into 0 minus 4 into 0. A into 0 minus A means minus 25 into 0 minus B into 0 means 4 into 0 by minus 25 equivalent to 0. So A equals to minus 25, B equals to 0, C equals to 500 and D equals to again 0. This is the Routh table. Then put A, B, C, D and final table. What is the final table? In this case, this is the final table. 1, S cube 100, S square 4, 500, S to the power 1 minus 25, 0 and S to the power 0, 500, 0. This is the Routh table, final Routh table. A equals to higher, A equals to already discussed, A, B, C and D. A equals to minus 25, B equals to 0 and C equals to 500, D equals to 0. Then Routh Stability Criterion. This is the characteristics equation. The necessary and sufficient condition from the Routh table. What is the Routh table? Row 3, row 2, row 1, S cube, S2, S to the power 1, 100, 4 into 500, 4, 500 minus 25, 0 and this is the first column. 1, 4, minus 25 and 500. This is the first column. So what is the conclusion? For a system to be stable, it is necessary and sufficient that each entry in the first column of Routh array constructed from the characteristics equation be positive. Our condition, this column, that means 1 positive, if 1 positive, 4 positive, 25 positive and 500 positive, then system will be stable. But in this case, this is minus 25, this is minus 25. So necessary and sufficient condition not satisfied. And what is the final conclusion? What is the final conclusion? This is step 8, stability analysis for the Routh table. From Routh table, this is the Routh table. And in the first column of the Routh array, there are 2 changes in sign of the elements. This is a very important sentence. In this case, 2 sign changes. Number 1, 42 minus 25, because 4 positive minus 25 negative. And again minus 22 to plus 500. So 2 sign changes. In this case, 2 sign changes. 42 minus 25, 42 minus 25, and that means plus 42 minus 25 and minus 42 plus 500. It is concluded that the system has 2 roots with positive real part and such that the system is unstable. So what is the conclusion? In this case, 2 roots right hand side of the S plane. This is the right hand side. So right hand side of the S plane, if this is real and this is imaginary, then this section right hand side and this is the left hand side. In this case, 2 changes in sign of the elements, this to this and this to it, is concluded that the system has 2 roots with positive real part and as such that the system unstable. System unstable. Thank you.